Welcome to this lecture on gas power cycles. So we will look at Brayton cycle, and that is the cycle on which your gas turbine power plant functions. So you can classify the gas turbine power plants into two types. One is your open cycle gas turbine power plant, and the other one is your closed cycle gas turbine power plant. So if you look at the images over here, so here you have the open cycle gas turbine power plant. And so there are three major components here. The first one is your compressor. So the second one is your combustion chamber. And the third one is your turbine. So in the compressor, we take in air. The air is compressed to a higher pressure. And the compressed air, together with fuel that is added in the combustion chamber, and when that ignition is given, the combustion process completes. Either it is going to be complete combustion or incomplete combustion. And the combustion gases, those combustion gases with the heat energy possessed in it, that is taken to the turbine. And so those combustion gases, the heat energy that is there in the combustion gases are utilized for running the blades of the turbine, which is taken as your work output. So the heat energy from the combustion gases gets converted into your work. Okay. And the combustion products after the completion of your work that is being exhausted to the atmosphere. So this is your open cycle gas turbine power plant. Instead of sending it to the atmosphere, if those combustion gases are recycled back to the compressor with the help of a heat exchanger, where you have a heat exchange, where you have the heat rejection process, then that is called a closed cycle gas turbine power plant. So we can say that this guy over here, that is state point number 1. So air enters the compressor at atmospheric pressure and temperature. Once it is compressed, it enters the combustion chamber at state point number 2. And then you have got heat addition, and that heat addition, after heat addition, the state point is 3. And the exhaust of the turbine that is taken as state point number 4. Okay. And so if we list the processes here, so process 1, 2, that is going to be isentropic compression, which is reversible adiabatic compression. So the first process 1, 2, that is isentropic compression. Process 2, 3. So we have already said that that is heat addition. But what we need to look at is what type of process it is. So that is constant pressure heat addition. Okay. Then we have process 3, 4 that happens in the turbine. So that is going to be isentropic expansion. And process 4, 1, in case of a closed cycle gas turbine power plant, that is going to be constant pressure heat rejection. So these are the 4 processes that we have, and this cycle is called as Brayton cycle. Okay. So now if we look at the PV diagram for this, so you have pressure on the y-axis and volume on the x-axis. So what we need to know is this particular Brayton cycle. Let me change the color to indicate the pressure levels. So it operates between 2 pressure levels, the higher pressure P2 and the lower pressure P1. So it operates between 2 pressure levels. And the first process that we have here is the compression process. So that is isentropic compression, that is process 1, 2. Then the second process, what we have is constant pressure heat addition. So that is going to be 2, 3. And then we have got 3, 4, which is expansion. And that is going to be isentropic expansion. And then what we have here is constant pressure heat rejection. So that makes your Brayton cycle in the PV diagram. Okay. So to indicate the heat addition and the heat rejection process, we can show that this is your heat supply here. And this is going to be the heat rejection. So we can say that it is QR. So QS is heat supplied and QR is heat rejection. So that is your Brayton cycle and the PV diagram. Similarly, we can also draw the TS diagram. So let me see if we have got space here. So this is your Brayton cycle as I have shown here. Process 1, 2 is constant isentropic compression. 2, 3 is your constant pressure heat addition. 3, 4 is your isentropic expansion. And 4, 1 is constant pressure heat rejection. So here they have showed this as Q in and Q out. However, the general notation is QS for heat supply and QR for heat rejection. However you wish to call, there is no hard and fast rule for that. Okay. And for isentropic process, we usually represent this as PV power gamma equal to constant. Okay. And these processes 2, 3, and 4, 1, that is going to be pressure P equal to constant. So for process 2, 3, and for process 4, 1, it follows the law pressure P equal to constant. And this is applicable, PV power constant is applicable for process 1, 2, and process 3, 4. Okay. And so if you look at the corresponding TS diagram for that, 1, 2 is going to be isentropic. So you have got 1, 2 as a straight line over here. So for this case, S1 is going to be equal to S2. Entropy is constant, and that is why we call it as an isentropic process. So isentropic compression. So temperature increases during a compression process. So 1, 2 is the isentropic compression. 2, 3 is constant pressure heat addition. 3, 4 is again isentropic expansion. So you can look at it over here. So this guy again, S3 is going to be equal to S4 because S is constant, and 4, 1 is constant pressure heat rejection. Okay, so these are the PV and TS diagram for your Brayton cycle. Okay, so this is an ideal cycle. What I have shown you here is an ideal cycle, and there can be deviations from the ideal cycle. So what are those deviations, or what makes these deviations to happen? The first one that you can see is the frictional effects. The frictional effects, one thing is it can be during the process 2, 3, and 4, 1, that is during your heat rejection and heat addition process, there can be a pressure drop in that, which means this P equal to constant is no longer P equal to constant. There is going to be a deviation in the pressure. Okay, so either your 2, 3, so this can slightly drop a little bit, and your 3 may shift somewhere down over here. And similarly, when you have a pressure drop during the heat rejection, your 4, 1. So you may have pressure drop once again. So, so that is your P1 minus P4. Okay, so you can have a drop in pressure. So it is no longer constant pressure process. That could be one frictional effect. The other frictional effect that can happen is in the compressor and the turbine, which can be shown in the TS diagram. Okay, and that is what you will be seeing in most of the problems that we deal with in our gas turbine power plants. So there will be a deviation from the isentropic process. It is no longer reversible adiabatic, it becomes polytropic. Okay, so they call this 2. So now 2 becomes 2s. 2s, S stands for isentropic. So 1, 2s is isentropic. And if you have a deviation, then your 2 shifts somewhere over here. Similarly, this 4 becomes 4s. And that is the ideal process, which is isentropic. and 4 shifts to somewhere over here, that is your 4, which is on the constant pressure line. Okay, so 4 1 is your actual process, and 3 4 is no longer isentropic, but it has become polytropic right now. And then the constant specific heat value which you use, that can change, that will increase with the increase in temperature. So these are the deviations that can happen from the ideal cycle. Okay, and the effect of irreversibilities, this is what I showed you there. So your 3, so in the TS diagram, they have shown you the shift in 2 to 3. So it's no longer a constant pressure line. So from 3, the 3 which could have been here has shifted to this position. And you can see that 1, 2s is the isentropic process, and 2s has shifted to 2. 4s has shifted to 4. And you can see that there is no change in 1, but because of the 4 has shifted from ideally it would have been here in the constant pressure line, but now it has shifted to a line which is away from the constant pressure line. Okay, so they have, so the first picture, it shows all the 4 processes are irreversible. And the second picture, it shows only the irreversibility concerning your isentropic compression and isentropic expansion. And most of our problems will be of this second picture. Okay, so where your isentropic efficiencies of the compressor and turbine are given. So let me introduce that also to you. So what will be given to you in the problem is they would give something called as isentropic efficiency of compressor, and that is denoted by eta C. Okay, so you can see that 1 2s has shifted to 2. Okay, where will you have the maximum work? Remember, for the compressor, it is V who give the work. So it is the work input that has been given to the compressor to run the compressor. So it is usually the actual work input which is higher than the ideal work input. So W ideal divided by W actual, which means ideal work input divided by actual work input. Ideal means the isentropic process. So if that is the case, then this can be written as, okay, I haven't introduced you to the derivation of the efficiency of the Brayton cycle. So once we do that, let's come back here. So let's stop with this definition and let me expand this a little bit later. So since we have started it, let's also look at the isentropic efficiency of turbine here. So isentropic efficiency of turbine. So what is the deviation of this work output with reference to the irreversibility? So your W actual will be lesser than the W ideal in case of work delivery. So let's define, sorry, this is supposed to be T. The subscript is supposed to be T. It is isentropic efficiency of turbine. So it is W actual divided by W ideal. Okay. So let's look at the derivation of the efficiency, and then let's come back to this definition of the isentropic efficiency of compressor and turbine. Okay. So remember the cycle that we had. So we had 1 2 is our isentropic compression, 2 3 is constant pressure heat addition, 3 4 is isentropic expansion, and 4 1 is again constant pressure heat rejection. Okay, now we know that the derivation of efficiency is always going to be written as W net divided by the heat supply. Remember the general formula that we used to have? It is the desired effect divided by the work input. Not the work input, just the input. So in this case, the input is heat supply. So let's simply call it as input, desired effect by input. So it is W net divided by heat supply. The desired effect is the output work that we get out of the turbine, and the input that is given is the heat supplied in the combustion chamber. Okay. So now how do I write this? So if I look at W net, there is going to be the work done in case of the turbine minus the work input that is given to the compressor. This is going to give me the W net. So if you look at turbine, so the expansion is going to happen in case of the turbine. And so I'm going to write the equation WT in terms of mCp times the process is 3-4. So this is going to be T3 minus T4. You may wonder why I'm writing this, because this is supposed to be isentropic expansion. We have a different equation for isentropic expansion in case of a closed system. Now we are talking about an isentropic expansion process that happens in an open system. So here the turbine is treated as an open system. So if you take this turbine, let me explain this for the turbine, and the same holds good for your compressor as well. So this is your turbine. The entry for turbine is going to be state point number 3, and the exit is going to be state point number 4, isn't it? So here, let us assume that it is a perfectly insulated turbine, which means there is no heat that is entering into this turbine once the the combustion gases have entered into the turbine. There is no heat that is entering into the system from the surroundings, and there is no heat lost from the turbine to the surroundings. Okay, so Q happens to be 0. And we assume that the changes in the kinetic energy is negligible. And also the changes in potential energy, they are also considered as negligible. So if you apply the steady flow energy equation for this case, what you have is simply W is H3 minus H4, which is nothing but, or if you are going to say that this is supposed to be multiplied by the mass, so it is M times H3 minus H4, which is simply MCP times T3 minus T4. So the same thing holds good for your compressor also. So if you take compressor, so WC, that is going to be MCP times T2 minus T1. Okay, so your W net, that is going to be MCP times T3 minus T4 minus MCP times T2 minus T1. And so if we take this M and Cp as common, what we have is T3 minus T4 minus of T2 minus T1. This is what we have here. Okay. And then let's concentrate on the heat supply. So let me use capital Q because we are multiplying it with a mass. So this is capital QS. So that happens in process 2-3. So that guy is going to be MCP times T3 minus T2. So now if we apply the equation for efficiency, which is W net divided by the heat supply. So what you have is MCP times T3 minus T4 minus of T2 minus T1. That is in the numerator. And in the denominator, we have got MCP times T3 minus T2. So if I cancel out these two guys over here, what is left out is T3 minus T4 minus of T2 minus T1 whole divided by T3 minus T2. Now what we are talking is about an ideal Brayton cycle where there is no irreversibility. So let's make that very clear. If there is going to be irreversibility in that, then that also needs to be taken care of, which we will look at while solving the problems. Okay. So now let's focus on some of the processes that we have here. Okay, let's look at process 1, 2. If you look at process 1, 2, that is isentropic compression, which follows the law PV power gamma equal to constant. So I can write this guy as P1 V1 power gamma is equal to P2 V2 power gamma. Or this can be written as P2 V2 power gamma. So P2 by P1, that is V1 by V2 to the power gamma. So if I apply the ideal gas equation of state over here, P1 V1 by T1 is equal to P2 V2 by T2 over here. And if I try to find an expression for T2 by T1, that is going to be P2 V2 by P1 V1. And so let's do this for V2 by V1. So V2 by V1 is going to be equal to P1 by P2 whole to the power 1 by gamma. So we already have P2 by P1 over here multiplied by P1 by P2 whole to the power 1 by gamma. So that is going to be P2 by P1. So if I add the powers over here, so P2 in the numerator has got the power 1 by gamma, in the denominator has got 1. If I take it to the numerator, then I have to subtract it with -1. So it is P2 by P1 whole to the power gamma minus 1 by gamma. If you remember, in the previous slide, we have seen that this Brayton cycle operates between the pressure limits P2 and P1. So we can define something called as the pressure ratio. And this pressure ratio can be defined as Rp, which is nothing but P2 by P1. So if the pressure ratio is P2 by P1, which is Rp, now I can say T2 by T1 is Rp to the power gamma minus 1 by gamma. Or I can say T2 is T1 times Rp to the power gamma minus 1 by gamma. Okay, so this is while considering process 1, 2. Similarly, we can also write for process 3, 4. If you look at process 3, 4, I can follow the same procedure and I will be able to write T3 by T4 is equal to Rp to the power gamma minus 1 by gamma. Or T3 is T4 times Rp to the power gamma minus 1 by gamma. So I would encourage you to follow the same steps as I have done for this process 1, 2, and you will be able to derive this. So if this is the case, now I will be able to substitute that in this particular equation. So eta is T3 minus, or let's substitute for T3 over here. So this guy is T4 times Rp to the power gamma minus 1 by gamma minus T4 minus T1 times Rp to the power gamma minus 1 by gamma minus T1 whole divided by, so let's say for T3, I'm going to write it as T4 times Rp to the power gamma minus 1 by gamma minus T1 times Rp to the power gamma minus 1 by gamma. Okay, so let me use this space over here. So your eta becomes, so if I take T4 outside, that is going to give me Rp to the power gamma. Let me write it a little bit down. So it is Rp to the power gamma minus 1 by gamma minus 1 minus T1 times Rp to the power gamma minus 1 by gamma minus 1. And here, if I take Rp to the power gamma minus 1 by gamma outside, I'll have T4 minus T1. And the same thing happens here also. If I take Rp to the power gamma minus 1 by gamma minus 1 as common, then I would have T4 minus T1 whole divided by Rp to the power gamma minus 1 by gamma multiplied by T4 minus T1. So I'll be able to cancel out these two. So what is left out is, so now what we have is, so if we write it, so we will have 1 minus 1 by sorry, let me write it over here. 1. So Rp to the power gamma minus 1 by gamma by Rp to the power gamma minus 1 by gamma is 1. Okay, so 1 minus 1 by Rp to the power gamma minus 1 by gamma. Okay, so that is what we have as efficiency for the Brayton cycle. So if you want me to write it a little bit lower for visibility's sake, so efficiency is 1 minus 1 by Rp to the power gamma minus 1 by gamma. So we have seen something similar or very closer to this when we talked about Otto cycle in our unit 1. So if you remember the efficiency for Otto cycle, let me use another color over here. So efficiency of Otto cycle is 1 minus 1 by R to the power gamma minus 1. So we had our Otto cycle, which was dependent only on the compression ratio and the specific heat ratio. Now we have the efficiency of the Brayton cycle depending only on the pressure ratio and the specific heat ratio. But once again, I want you to be very clear on this. This particular equation, the efficiency of the Brayton cycle, where you say 1 minus 1 by Rp to the power gamma minus 1 by gamma, this guy is applicable only for ideal Brayton cycle, which means all the processes are reversible over there. Okay, if process 1, 2, and 3, 4, if they say that there is going to be an isentropic efficiency of the compressor or isentropic efficiency of the turbine, then this particular equation is not applicable when there is irreversibility mentioned in the problem. If there is going to be irreversibility in your gas turbine, that is your Brayton cycle, then this particular equation cannot be applied for that particular scenario. So having written the expression for work input to the compressor and work delivered by the turbine, let's come back to our isentropic efficiency of the compressor. So your ideal work input to the compressor, it will be MCP times. Okay, so if it is going to be ideal, it is going to be process 1, 2s, isentropic. So that is going to be T2s minus T1 whole divided by MCP times T2 minus T1. So if you cancel out this MCP and MCP, so it's going to be T2s minus T1 divided by T2 minus T1. Similarly, for your turbine, that is going to be MCP times actual is going to be T3 minus T4 whole divided by MCP times T3 minus T4s. So if you cancel out this MCP, so it's going to be T3 minus T4 divided by T3 minus T4s. Okay. So this is these are the fundamentals that needs to be remembered while solving the problem in case of your Brayton cycle. Thank you.